So welcome to our next tutorial on Docker containers. And today we are going to talk about data transfer between host and container and container and container. We are going to cover three basic modes. First one, and we are going to start with that, how to provide the environment which Docker which serves only as an environment, and how to copy files from your local system to this Docker container using the copy cp command. Next, we are going to talk about how to sync the data from your local file system to the Docker using Docker bind. And finally, the most general case, how to sync data between containers using Docker volume. Let's start with our first example. How to provide an environment which hosts only Docker, which has only a runtime environment, no files within there. How to transfer the data from your host to your local computer to the container image. But before we start, let me explain you my toy example we are going to use in this and next tutorials. I have created a simple set of two applications. These are hidden here in my app subfolder. As you can see, I have some run file which has paths to the corresponding app1 and app2 folders which contain my simple toy application scripts. This file just simply calls those programs using subprocess call. This is the Python module which enables you to run external scripts, external Linux commands from within the Python. So as you can see, I have some program list, program 1 and program 1 path and program 2 path, and for program in this program list I call those in a sequence. So the first call is to app1 slash app1.py, and second one is app_2 slash app_2 py. So when we look at those two folders, you will see that I have in the app1 input and output folders which are empty at the moment, and app1, which is extremely simple script which prints out that the app is started. Next, checks if there is something within an input folder. If it is not, it creates some fixed pandas data frame 2x3, 2 rows, 3 columns, saves this to this folder, and next checks for generates some random number, prints that number, multiplies this original data frame by this number, and assigns this to the df_out output data frame, and store this in an output_1 CSV file in the output folder, and prints, okay, I did the transformation and the app1 is completed. The second app takes this data from, as you can see, app1, so it's here, and output, which is there, yes, this input, and once again, if there's nothing there, it generates its own data frame, but we assume that when we run them in the sequence, there will be something generated by the app1, and does almost the same. It's also chooses generates some random number in the range of from 1 to 5, but this time it does not multiply the input data frame, but adds this number to the data frame just to have a different actions at hand. The first one, app1 multiplies by some random number, and app2 adds some number, and once again prints that out on screen and saves the result into the output_2 file in the output folder of this app2 app. So this is a very toy example, but it has some sense because if we treat app one as a component in our machine learning pipeline, as you can see, it has some input, it does some job, it generates some output, and later then app underscore two is another component which reads the result of the component one, application one in our case, and also does some other transformation. Okay, this is just choosing and adding an extra random number to this, and once again save this output. So this is the very the most simple example of the pipeline I could imagine, but it's that easy that with those printouts we can really control whether our pipeline which is a combination of those components artifacts, works with Docker, and whether the Docker data transfer works as we expected. So once again, very important, very easy example, which I'm gonna use for our next lectures. And in our case, in your machine learning case, you just simply substitute the app one, app two by, for example, the script which prepares data for modeling or trains the model, yes? But as always, it will have some inputs and generate some output. So that's all about our toy example. I'm not gonna cover this topic later on. It's self-explanatory. And now let's dive into our first example. We are going to create a container that only provides a runtime environment. Okay, so we are here. Let's have a look at the structure now. Let's have a look at the Docker file. It is extremely simple. So at the moment I use a very basic slimbuster image. For this image, pip install works correctly. There is no problem with finding that very simple basic version of pandas I require for this purpose. So that's why I'm using this Python. If you need some higher version of pandas, that might generate some problems, and in that case, don't worry, just simply use Ubuntu or some other tweaks on updating, for example, pip in this case. So as previously, let's build this image now with the following command. So docker build -t bind underscore app1 underscore 2. It's gonna be the name of our local repo for the image. Tag is v1, so this is the version 1, the name of the tag. Let's build the docker. Okay, so it's there. So now we can run the image locally. So let's run this docker locally and see what happens. As you expect, it won't run the code, yes, because there is nothing to run. It just simply have the environment installed. So let's run it. Let's see. Oops, as you can see, it calls simply the Python here. And in case I, for example, write import pandas as PD here, as you can see, it generates no error. So that means that the Python called in this by this Docker contains pandas installed, so the Docker file that did its job. So let's continue. Exit. Let's make the exit. Oh, maybe we'll just leave it here and start a new container, a new bash terminal. And in this terminal, now we are going to try to copy the files from our local file. Let's have a look. We need to change the folder to 4.1 folder, which contains what? It contains the Docker file we started with, and also contains my app folder with app1, app2, and runpy subfolders. So now we are going to copy the files from our my app folder to the container, which by the way runs somewhere in the background. Yeah, so it runs in the background. Let's call this exit here. Yep. Okay. So let's do it the following way. In the new terminal, in this terminal I'm gonna run the terminal, this our image, but as you can see, I have this bash command here. So now, as you can see, I'm within this container created using the Docker file, which we can see at the top. It has pandas installed already in this environment. So in another terminal, let's try it here. Okay, we are going to check with Docker PS our running containers. Yes, I can see, as you can see, I have this container running. This is the image name. This is the command which is running. Okay, it started 29 seconds ago, and this is very important for us because this is the container ID. So once again, this is the ID of this container which runs here. Okay, because here we are within the container, which is the app which is running. By the way, as a cross check, we can check if it's running. Yes, it is running here, as you can see in our Docker plugin in Microsoft Visual Studio Code. So we can control it from different using different tools, command line interface as I do now, or Docker within Microsoft Visual Studio Code. And now in this terminal, I'm gonna I have, let's see, ls, yes, I have my app folder here, and now I'm gonna do the following. I'm gonna do docker cp, that means docker copy my app, which is the folder, yep, and I will copy this to this terminal. What was the container ID app? It is container ID. So I copy paste this container ID here, and here I just simply say, okay, just copy this folder to this container colon and the folder app in this container. Okay, so that means, okay, just copy my app from my local file system to the /app folder within the container with this ID. Okay, it has successfully copied this, and now we can come back to our container, and once again with ls, if I type ls here, yes, I can see my app. So previously there was no app. Now if I go to this, I can, as you can see, I have this running, and now having those files copied from my local file system to the running container, I can type, for example, Python 3 run by and see what happens. Yes, it's done. As you can see, it has correctly called a sequence of applications using the subcall. Once again, let's have a look. This is run by. It calls subprocess, which, as you can see, starts the app number 1. App 1 has started. This is the original data frame. This is the random number chosen. This is the multiplied version. So as you can see, 10 times 2 makes 20. And then it's completed. And then application 2 has started. And as you can see, it reads correctly from the dead folder, which is, by the way, as you can see, on our local system, it's empty. But on the system of the container, within the container, it's not empty because all the process has started from this container. So it says, okay, my original data frame, application 2 tells you was this one, which is, by the way, the output of the previous container, yes? And then I decide to choose this number 2 and then transform it by adding this number to original data frame. So as you can see also the power of the simplicity, because we can see that was the artifact number 1, this is the action, and this is the output of the artifact component number 1, and then it's transferred to the component number 2, application 2. This is the action, and this is the artifact, the outcome, output of the component number 2. And now we can check, for example, here for ls, and then go to app 1, for example. And now, as you can see, we can check, go to output folder, and we can see we have something. So I can check more output 1. As you can see, we have this comma separated file. So we did it. We have successfully run the container, and we have copied the data from our local system using cp command, and then we were able to run the container, the program copied from our local system to the on the container, yes, and our original Docker image had nothing, had no files in there. So so that was CLI, a command line interface, a way of doing these things, which is most common in the production-ready environments, because you can create different shell scripts for that, make it more advanced. But in case you would like to play with that on your local machine, you can also experiment. I leave it up to you. As you can see, we have images here. We have this image there. Nope, it's not one. This is the yep. So that was bind one, up one. Yes, but this is the image. Okay, so you can try to. Yes, these are the files, as you can see. This is these files. You can also try, and I leave it to yourself, to copy files from your local file systems to this, for example, by drag and drop. Just have a file, try it, test it if it works. If it works, you'll have another way of doing things, copying files between your local file system and the running container. So now let's talk about another solution which might be useful in some other use cases. Our previous container image didn't have any files at all. We had to copy those files from our local system to the container in order to make it working. Now we are going to do something opposite. We are going to create an image which contains all the required files. There are plenty of different applications of that. For example, you would like to provide the user with all the code and all the libraries required for running the script, all the data, but also, for example, you would like someone to test your app, which is the website, working with some database in the background like Redis, PostgreSQL, or MySQL, and you do not want someone to install all those databases. Yes, so you create the image which contains not only your app but also the required database, all the data sets, etc., source files or data which are read. Then you provide the user with the whole Docker file which runs completely without any requirements from the user. So let's do it. Once again, we have this toy example. As you can see, this is the same example. A Docker file is here, as you can see. Compared to our very first application we did in this course, we do not have this command at the very top, at the very bottom. So when we run this container, it won't do anything, but fortunately it will also not leave us with a stopped container as a kind of the overhead. Yes, so that's quite clean Docker in that from the maintenance point of view later on. So as previously, let's build the image. So we are going to use this command for this. This is the command. What has changed? As you can see, I use the same. Oops, apologies. I use the same repo as previously, internal repo bind up1 underscore up2, and a tag. A name of the image here is v2 for version 2. Yes, so let me build this. And now what I'm gonna do, I'm gonna invoke the following command within this container, not container, but in our system, docker run. Okay, once again, minus -doi flag. Then this is the name of our image. But later then, as you can see, I call python 3 run py command from this container. Yes, so this is the option of moving this running command, yes, from the Docker file to our local system. So in that case, as you can see, yes, everything is done. So once again, let's have a look what happens here. I call docker run, but not the single image because it won't do anything. But I say, okay, take this image, make the container out of this, and then within this container run this command. So it does the job because this container has all the files inside. All the files inside. This is thanks to this copy all the local files, including this up1, up2, and runpy. Yes. To this working directory. Thanks to this, within the image we have all the data, and we can run this script which is available in our final directory from here. Okay, so this is very simple, but still very useful. Now it's time for a bit more advanced method, a very powerful method which enables us to sync content of our local folders with container folders. We are going to use bind mount mechanisms of Docker. So let's have a look at our toy example. We are now in this folder 4.3. Once again, this is the same toy example we had. Look, we have no input and output data in our up_1 and up_2 folders. It's completely empty. Our Docker file looks like this. This is once again, this is very simple. Linux Slim Buster distribution, which simply installs only the pandas and copies the files from the local folder during the image build to the app working directory within our image, later on container. So now, so there is no change compared to previous versions. The only change will be in running the container itself. So this is very important. There's different scenarios will differ only by the run command parameters. So let's build the script at the moment, build the image at the moment using this v3 name. This is the version 3 of our image, just to work step by step. By the way, as you can see, I'm using my base Conda environment, which has nothing installed. It's completely clean. I do not need anything installed here because I have Docker daemon running in the background, which does the job for me. So let's build the image. Okay, so the image is being built. So once again, now let's have a look at this local file system. As you can see, it's clean at the moment, and at the moment I'm gonna run our Docker container with the following command. Let's have a look at this command. We have docker run as previously, but here there's a new entry, yes, minus volume, and I take a local variable name present working directory. Yes, this is the Linux command. So I say, okay, take the value of the present directory. In my case, this is my local Mac directory. Okay, and mount this directory to the app directory of the container. So there is a mapping. It tells me, okay, map my local folder to the app folder of the container. Yes, and with this option -v and the mapping, run this container, precisely speaking, run Python free run py within this container. Okay, so this is precisely the same we did on our previous case, but now we ask Docker to sync the data between one folder and the other, local folder and the container folder. So let's give it a try. It's there, so it was run within the container as previously, but look what happened here. I have input and output files here in my local folder, so the container did the job locally, and later then it synced the content of the app folder with my current folder. Yes, because this is my current folder. So I have the sync. So this is the first way. Okay, so I took the data from the container to my local system, but I can do also opposite, which is very handy for developers. For example, I can modify this script now. I will add a command like, for example, print hello, hi buddy. Okay, hi there. I am a run py file. Okay, so let's run this. So now I modify the script on my local folder. Okay, and let's run it once again. Let's have a look what happened. What's gonna happen? I can run. Yep, as you can see, at the very top of this, I have this command. So the typical use case is the following. I want to present my work to some other developers and help them to work on my original code, and they are able to change this code from their file system. Or I want to move my work from one computer, which I have in my office, to home. By the way, I do not work at home, yes? Home is just for fun, but still from one office to the other office, yes? So I just simply take a job with me, yes? So I have a full sync between one computer to the other, and the container is synced with my current job. So that's for developers. That's also the sharing. You can use that for training, so you can provide students with or trainees with some original data, then we'll sync the data with their computers, but later then they will be able to play with their own data, so they are not only forced to always use your own data. They can change the code, they can change the data sets. So this is another very important use case. And now we are ready to make another step, a big leap into machine learning pipelines with containers. We are going to use volume mount mechanism from Docker. Until now, we were transferring data between host and container. using either using during the firstly building the image stage, next using cp command, or syncing the local file system with the container. Now we are going to create the mechanism which will enable us to transfer the data between running containers without touching a local system. Okay, without touching the local system. And for that, Docker developers created the Docker volume. So we are going to, I'm gonna show you two different examples. First one with the single app with volume mount, and second one, many containers. For the first case, we are going to use a very simple application which reads some data from data folder, yes, with a single, creates a single data frame as previously, generates some random number, multiplies this data frame by this number, but as you can see, at the result, it will output this data frame, and this is very important here, both to the input path, which is this original path with the data, and to the output. This is just for that for the next run of the container, it will help us to make this next run a continuation of the previous run. So imagine we have a single container, okay? You provide it with some input. It transforms some data, creates a new output, okay? And it stopped. And we once again run this container, let's say after the day. So it will take this output of the first run as input to the second run for the same container. Yes, so that's why I needed to make this. I had to make this some tweak with this, saving this data both to the input and output path. So let's do this. Let's build the image with the following command. And now I'm here, docker build -t, and now I change a local repo for this. You can treat it as a name of the your container, app1_vm volume mount, and then I have a tag, a name of this image within this repo as v1 version 1, and once again space and dot, which means take all the data including the docker file from the existing folder, the current folder. This is once again a very simple docker file. The requirements are also very trivial, it's only pandas. Within this docker file, as you can see now, I keep this command cmd command python3 app1py. So once again, as you probably recall, it will run the container, stop the container, but will keep this container, yes, in our system. So, but let's build a Docker image with that. Okay, it's there. So now the next step will be to create a Docker volume to be accessible later on for our running images. So I create this Docker volume with this command, Docker volume create. So create a kind of the virtual drive, virtual volume in our system. And name this a volume with VM underscore app1. So it's created. And by the way, we can check it now in our Docker plugin. So as you can see, I have volume sections here. If I click it, it's there. Okay, this is our volume, virtual volume. Okay, so let's come back. And now we are going to sequentially run our image. So let's have a look at this command now. This is the command. Docker run -ti -v option, and now, as you can see, we map, instead of the local file system, which we did, a local folder, current folder, as we did with bitmount, we have this virtual folder. Yes, so this is the volume created by the system. Okay, I wonder if it's gonna work. Let's try. I mounted to this local container file up. It's okay, that's correct. So as you can see, it's there. So it created a new data frame, has chosen the random number, and created the transform data frame. And now let's have a look. Let's check with Docker PS whether we have some containers running, just to check. No, there is no containers running, but let's have a look at this stage now. I'm gonna run this image once again. And look what happens. The original data frame, which is the input to the new process, is precisely the same as the output of the previous one. Okay, so now let's try it once again. Once again, the input to the next container run is the same as the output of the former run. Okay, but it was multiplied by random 1, so once again, let's have a look. Yep, this is here. Perfect, and once again, it's there. So we have the continuity achieved. So subsequent container runs use the results of the previous ones. What are the typical use cases? First one, I already told you. I want to ensure the continuity of my application so that subsequent container runs with my application can use the results of the previous ones. Another use case is I want different containers running in parallel to exchange data. Yeah? Or I want to store the data used by my containers with a cloud service providers. So these are many different use cases for that. So we are almost there. We are ready to create an application with many containers. Precisely speaking, at the moment we are going to use volume mount to enable two separate containers to share data. So let's have a look what do we have in our current folder 4.4.2 of my files. Obviously, you have all those data, the scripts in your shared folder. We have app1 and app2, but now as separate containers, separate Docker projects. Yes, so we have application 1 with the corresponding Docker file and this command run at the very bottom. So once again, if you build and run such image, it will run the app1 script from this folder. And we have a separate Docker project, I would say, which we'll create a new separate image for this, and we'll be able to run this as a separate application. So imagine that we have two different applications from two different providers or two different components created by different teams or by yourself, yes? And you wanna combine them and make them exchange data. So exchange in a way that, for example, the result of the container 1 up from application 1 will be used as the input for work by the container 2, application 2. So we have component, but now these components are separate Docker containers. So let's do it as previously. We are going to start with building the containers. So in order to do this, I firstly go to app_1 and build the Docker image here, which I'm gonna name as app1 shared version 1. So let's build this. Okay, it's done. So now I come back to my main folder, go to app2, yeah, and now call almost the same command, but with app2 here. That's gonna be a separate Docker image. And just to check, if we go back to app1, and if you would like to run such an image, we need to type the following command just to check whether it works correctly. So as you can see, I just simply docker run this. Yep, it's done. And in a very similar way, I will run the app2. By the way, I didn't have to change the directory for this, but still I did it. You can run the Docker from within any folder. Yep, it's there. So, but now they are independent. They do not share the data. So how to make them share the data? So we are going to once again reuse the mechanisms of Docker volume. Yeah, and then we use Docker volume 1 from Docker run command. So now we are going to create a Docker volume, which we will name volume underscore app1 underscore app2. So it is created, okay? And now we are going to run those applications in a way that they will sync their results, input, output, with the volume mount. So let's start with running the first app in that way. So let me come back to the main folder. And it's not necessary, but still, look what happens here. Docker run -1. So now I map this newly created Docker volume to data app folder. Yes, so, and I'm calling app1 underscore shared v1. So what's there? I'm calling this Docker image. Yes, I'm running this Docker image app1, and I map this shared volume with its internal storage. I did it in a way that the name of this internal storage is the same for app1 and app2. Okay, it's there. And in order to do this for the app2, I just simply change the image name. It's there. And now let's have a look at the result. Let's have a look once again. I will run Docker, the first application, app1. As you can see, it results with this data frame. Transform the F is here, has 40 and 1260 here. So that's why, by the way, I choose those random numbers to generate, because in case I would use a fixed numbers, I would never be sure whether the pipeline works as I expected. Yes, so that's why I use random numbers here. And now if I run the app2, as you can see, the original data frame for the app2 is the output of app1. So we have the continuity. Once again, let's have a look. Let's give it a try once again. So I call app1. It results with this data frame. By the way, as you can see, app1 doesn't take as input the result of app2. 2. The sequence is the following. Firstly, I call app1, yeah? And then let's try app2. And it is here. So the app2 takes as the input the output of the app1. So we are done. We are done. So we have a very, very simple setup where we have two different containers and make them exchange the data, but without touching the local system. So we can, specific case, put them in the cloud, put them into different servers, use Kubernetes to manage those servers, and still have a data flow exchange of artifacts in the pipeline realized. And this is very powerful. So I hope that this very simple example will open the doors for you for your future apps. Good luck.